Biphenol. Oh, so the fourth speaker is not there.
Yeah, it will be presented on site.
Yes.
Can you see my slide?
Hi, yes. The slide is not shared yet.
Not shared.
Not shared yet.
Is the slide shared?
Ah, yes.
So should I start? Or wait?
The installation was crowded, so maybe we can. It's the long queue, so maybe we can wait a few minutes.
Elisa, could you share?
Should I introduce him or?
Maybe just start.
Could you start to talk? Are you Amazon?
Yes. I can start.
What's your representation?
This okay? I will pass the speaker.
Okay. Text. Noise base. It's okay.
So And I want to start. First of all, thanks. I'm very glad to have a chance to give a talk here. And the title is the development and validation of the computational code GEM for simulating quantum field systems through optimization on the supercomputer product. And I belong to KK, and my name is Aoyama, Shigeyoshi Aoyama, and collaborators are Tsunoda, Shimizu, Matsuru, Kanamori, and Hian. First, I would like to explain our background and motivation. But I want to explain GEM code. GEM code with Gauss lobe technique is an established high precision method for free system. First version was made more than 30 years ago. And the existing code already solves 3 to 5 body system on the processor, on one processor, but state-of-the-art 5 body takes about a week at least for most simple case. We port it to Fugaku and parallelize it efficiently with the method unchanged. This is a benchmark talk. The helium for pentama, it is a 5-body typical 5-body system, already solvable on one node given time. But we want to the same result faster because we have to analyze helium for pentama. We have to repeat several computation with different parameters. And one-time calculation is more than 1 week. It means it's almost impossible to analyze. So this is background. And this is our strategy. This figure shows GEM code and our development. And GEM code is 5-body systems code. And in the previous conference, CHPC 2005, I report the development for machine kind of machine learning, and the present talk is massively parallel computing. And at CHPC 2005, we report SPM plus. It's kind of machine learning, and that cut memory used by about 99%. I mean, 0. Several percent memory is enough by using machine learning technique. And there are several remaining techniques, but in this area, I want to report massively parallel computing. The remaining about bottleneck is the cost of computing the matrix element. This CHPC 2026 presentation takes optimizing the GEM code for massively parallel computing on Fugaku. Here I want to explain GEM. That is typical technique, typical method to solve quantum free-body systems. We diagonalize the Hamiltonian in a Gaussian basis built on Jacobi coordinate. Gaussian width in basis function follow a geometric progression. And this is a Gaussian width parameter, and there are three Jacobi coordinate. First one is K plus 1 helium atom, and the second one is H type plus 1 helium atom, and third one is Tolima plus time type basis function. These are three types of basis function describe 5 body systems, and this is a basis function. And angular momentum part of the wave function is written like this. For angular momentums is coupled to each other like this. L1 is coupled to L2, and there is a L1, 2, and so on. And in this calculation, this is a kind of benchmark. So angular momentum, all angular momentums are set to 0 like this. And in that case, there are 3 channels. For K plus 1 channels is like this, and for H plus 1 channels is like this. And 3 plus 2 channels and is like this. And total angular momentum is 0. And for helium-4 pentamer case, these channels are very good because total angular momentum is 0. And I want to show numerical result. First, I include channel 1 for K plus 1 type configuration, and energy is 0.8 Kelvin, and the number of basis function is 31,000, about 31,000. And next, I include other channel for H plus 1. In this case, I get 1.2 Kelvin like this. And the total the number of total basis function is 43,000. And next is 3 plus 2 Tolima plus dimer type configuration, and in this case we get minus 1.3 Kelvin, and total number of basis function is 48,000, and this is not perfect, complete model space, but if we include other channels, energy is not changed. About full model space, 1.308 Kelvin. In the simple model space calculation is 1.303. So these 3 channels are enough to do benchmark calculation, and other group did similar calculation, and helium for atom case interaction is essentially same, similar. So their results are also similar, and minus 1.295 Kelvin by Bloom, and minus 1.300 Kelvin is Bazak. So the matrix element for this benchmark is very good. And I want to explain some problems for original gem code. The original gem code run on a single processor. As I say, this is firstly made about more than 30 years ago. In that period, there are no parallel computer. And after that, this code has been developed. And this code is known to be stable and precise, but never parallelized, and with no GPU or SIM. So naturally, it takes very computational time. Even a 5-body case run takes about a week at least. Its cost is almost entirely the calculational time of the matrix element, and which calculation of matrix elements are completely independent. So this is an ideal case of parallelization. So the speed up scales with the machine proportional one node. So 1,000 of nodes gives 1,000-fold speed up, and larger machine push its faster. Here, I would like to show the benchmark result. This is a simple MPI benchmark. As I said, the matrix elements are independent, so and each takes the same time. Ideally, the runtime falls as 1 over number of nodes. This is the ideal case. We parallelize with MPI over the channels and virtual channels. I will explain virtual channel later. Benchmark situation is 720,000 matrix element. This is channel 1, size to run in about 10 minutes on a single node. This is a small matrix element.
Hello, this is the share. You have about 3 minutes. Oh.
Okay.
Yeah.
That's enough. And this is the result. Blue line is speed up ratio. Horizontal axis is the number of nodes. In this calculation, I use 120 nodes, and the speed up ratio is nearly 120. This would be enough. Ideal line is dashed line. And the next benchmark is so-called hybrid parallelization, and dimension of matrix is larger than before. And I also calculate the matrix element, and this is a figure, and I'll line is a dashed line, and calculate result is a solid line. It's faster than ideal case. Maybe you think why our calculation is faster than ideal case. The reason is easy. Size of the matrix element is same, and 120 node calculate matrix element separately. And in that case, size of the matrix element in the same node becomes small. So cache works very well. In this calculation, I use a Fugak supercomputer. Fugak has a large cache, so matrix element hits cache. So speed up ratio becomes faster than ideal case. That is our result, main result. And finally,
Hello, you have about 20 minutes now.
okay, so I want to summarize. This is my summary. Thank you. Main result is speed of ratio. Thank you.
There any question? Maybe one question?
Simple clarification. Gaussian, the method name Gaussian comes from RBF, right? Radial basis function. Basis function.
Basis function.
That's why you use Gaussian radial basis function.
Yes.
So the name of the method is called Gaussian.
Gaussian expansion method. So we solve the relative motion with Gaussian basis function. We typically superpose Gaussian basis function about from 10 to 20.
And why denotes the spherical harmonics? In the earlier slide, you had letter Y. That means spherical harmonics.
Yes, because Peabody system has angular momentum. In this case, just zero. But generally, we need angular momentum between the particles 1, 2, 3, or something.
Yeah, I'm working on spherical harmonics and also the radial basis function method. So your talk was very inspiring. Thank you.
Okay. Let's thank the speaker. And can we have the second speaker?
Can you see my slides? No.
Yes.
Yes, on time. Can you help?
I can see.
It's shared. I should put. now you can see.
Could you change to the full screen mode? Oh, yeah, yes, okay. Maybe from the menu.
Is it full screen online as well?
No, now it's fine.
It's fine. Okay. Okay. Hello. My name is Takeshi Enomoto from Kyoto University. I'm going to discuss about global atmospheric model, which is can be generalizable to any direction on the sphere in any other fields. Advection is very important process in fluid dynamics, and especially in meteorology and oceanography and other areas like planetary atmosphere. There are two approaches, Eulerian, which compute the advection at each grid point and compute spatial derivatives there. And another method approach is mainly used by operational numerical weather prediction centers such as ECMWF in Europe or JMA in Japan. That is a semi-Lagrangian advection scheme that interpolates the value at the departure point. And there are desirable properties of the advection, which include high accuracy, monotonicity, but that does not, strange value does not pop up. That equals monotonicity and shape preservation. When the shape is moved, it should preserve that shape. And however, Aurelian and semi-Lagrangian schemes have their strengths and weaknesses. This study presents accurate interpolation method in semi-Lagrangian advection scheme and validate the new scheme in very challenging test cases on the unit sphere. So we consider two-dimensional advections on unit sphere. And here Q is a tracer and the V are horizontal winds, zonal, west-east, meridional, south-north. And in Eulerian scheme, is discretized this way, and considering the spherical geometry, and it requires three-time level in this scheme, and it uses spherical harmonic expansion to compute derivatives. And here, pi, theta, longitude, and latitude. And the weakness of this scheme is dispersion error and the limitation of time step to short time steps. Another method is interpolating semi-Lagrangian method. And here, G, red square, is a arrival point, the point you are looking at, and trace back, tracer back to the departure point R. And the wind is computed at midpoint. And that this is two-time level scheme, and it requires interpolation. So if the interpolation is poor, you get a very poor results. And there are also a non-interpolating semi-Lagrangian scheme, which compute the nearest grid point of the departure point, and I use this value just at the G, and residual are computed in Eulerian manner. So we compare Eulerian and interpolating semi-Lagrangian, non-interpolating semi-Lagrangian scheme in this talk. And the method commonly used by operational center is called quasi-cubic to reduce computational burden, which compute linear interpolation at the edges, two edges. And in the dashed lines, three dashed lines, they use Lagrangian cubic interpolation. and it omits the corner points. So it requires 12 point information to get the value at red cross point, the target point. And another approach is bicubic interpolation, which is often used in image processing. And the point here is computed from the 4 corner points. This is compact. The method I propose is a spectral bicubic interpolation. It uses the derivative at 4 corners, zonal and meridional cross derivatives, but computed in spectral space. So the accuracy of the derivatives are very good. It requires 16 value at 16, 4 points and a total of 16. And this is, as I said, bicubic scheme, so it is local. This is a configuration of the challenging test cases. It's a non-divergent deformational flow. It starts with, in this case, 2 tracer cosine veil, and it is stretched, and at maximum point, like the 2.5 here. And it goes back to the original position at time t5. And this has no analytical solution, but the initial condition is the reference. So you can compute error. For infinitely smooth twin Gaussian hill is the first case. This is a test case for convergence. It is in the horizontal axis, that is cos 3 degree to 0.1875 degree. That is resolution, current resolution of the model used by JMA, or double of the ECMWF. And 2 gray lines secondary and third order convergence. And red is a spectral bicubic method. It has a lower error and higher convergence rate, as you see. This is a CFL condition at 1. And at the larger CFL condition of 5.2, you cannot use Eulerian method any longer. So comparison are between a quasi-cubic and spectral bicubic non-interpolating, and the other one in brown is relaxed truncation wave number. So spectral bicubic has advantage, a little bit advantage at coarse grid to relax truncation. Another test is 2 cosine bells. Cosine bells have a jump around the tracer, so it is not infinitely smooth, discontinuity there. And this is a cross section, and you see that the quasi-cubic method has a dissipation error. The mountain is lower due to the interpolation, and spectral bicubic has a higher peak, and but it has a ripples at the tail. But if you relax the truncation, so it reduces, it suppresses ripples. And more challenging case is a 2-slotted cylinder. It has only 2 values here and here. There are 2, white and red, and there is a slot in the middle. And if you see them spatial distribution, this longitude and latitude at the mid of the integration time, and it is stretched, and it has a gap, still have a gap here. And the quasi-cubic method has limited ripples around edges, but the spectral bicubic has a small but global ripples around all in a computational domain. And this is a final time And you see that the colors are changing quite sharply using a QC. But a spectral bar cubic has smaller ripples. These features can be reduced. The ripples can be reduced by using a filter or limiter to suppress those noises. This empirical way to reduce those. And if you look at the cross section, you see the difference more. This is unlimited case without any filter, and the limited case with filters. If you use a quasi-cubic method, there's a large overshoots called Gibbs phenomenon. And SBC, spectral bicubic method, does have small ripples. You may not be able to see, but there are small ripples. If you use a limited model using a filter or limiter, it effectively suppresses those spikes. And finally, this is a mixing diagnostics. We deal with tracers such as moisture or small particles in the atmosphere. So it should maintain some functional relationships. And here in x-axis distribution called this distribution is related to this distribution by quadratic function. So ideally, his scatter plot should go along this green line. But numerical error results in a mixing, some kind of mixing. We divide mixing into three. That one is real mixing that imitates actual mixing in the atmosphere. And the other is range preserving mixing that not overshoots. And there are other kind of error that is called overshooting. This is outside of the domain of the tracing. So we
Hello, you have about 3 minutes left.
Okay. This is my last slide with pictures. And William has some overshooting, and quasi-cubic has even larger overshootings, and here and there. And the non-interpolating scheme also have a large error and remixings. Compared to existing scheme, our SBC has us very tightly distributed along this quadratic curve, and it has much smaller error nodes. To summarize, we propose a very accurate scheme called the spectral bicubic interpolation scheme, which uses derivative at all the corner and calculated in spectral space. And we validated this scheme in challenging two-dimensional direction test cases. We proved that our method, SPC, outperform Eulerian interpolating and non-interpolating Segregation scheme in several metrics, including convergence and suppression, Gibbs ripples, and mixing diagnosis. And we found that the relaxed truncation is spectral bicubic further improved accuracies. And we demonstrated that the quasi-cubic, which is used in operational numerical weather prediction, can be dangerous because it introduces detrimental error, and it is even worse than the Eulerian method. And finally, we show that the effectiveness of the limiters. And thank you very much, and I take any questions.
Any question? Okay, then we go to the next talk by Suzune Nomura and Takashi Enomoto. And that is on an efficient and stable solver for the shallow water equations on regular latitude, longitude grids using spherical Fourier transforms.
Good morning, everyone. I'm Sune.
Could you share the screen?
Sorry.
The slide is not shared.
Okay.
Sorry. I'm Sune Nomura from Kyoto University. The title of my presentation is Efficient and Stable Solver for the Shell-water equations on regular rational long-term groups using the spherical Fourier transform. First, let me briefly explain the background. Spherical harmonic transform are generally used for the fluid dynamics in numerical weather prediction models, and the major focus center including ICCSA in Europe and GMA in Japan. Recently, computational costs have tended to increase because of increase in resolution and the number of ensemble members. Let me explain the conventional SFT. SFT is as spherical Fourier transform. To reduce computational costs, there is a method that applies to the Fourier transform. Unfortunately, the spherical derivatives are computed solely so one-dimensional Fourier transform. The spherical derivative via the one-dimensional Fourier transform is calculated by forming the FFT in the long-term direction. Long-term direction as shown in the figure. For rational differentiation, the data are rearranged so that the array from the great circle passing through two poles. The derivative is computed the same way as in the long-term direction using one-dimensional Fourier transform. Each transform is independent, and thus this method is more easily parallelized than the spherical harmonic transform, SHT. We have two objectives in this study. First, previous SST has power singularity, so it generally does not allow allocates point to be located at the poles. For example, the derivative of longitude on the sphere based on SFT is this formulation. And this coefficient become infinity because sine theta equals 0 on the pole. Furthermore, more global graded data are provided on regular grids, including the poles. Then it needs to be rewritten in a form that does not diverge at the pole. The second objective is isotropic wave number translation program. Then calculates the nonlinear term using spectral methods, high frequency is interpreted for low frequencies. This phenomenon is called aliasing. To prevent aliasing, we need to truncate high wave number. This table shows the computational accuracy for different methods. Top to bottom, SHT method and combine FFT and SHT and only FFT method. The combined methods agree with SHT method, but only the FFT method disagree with the result of the SHT method and becomes numerically unstable. From these results, truncation based on SFT is not isotropic. To develop a stable computational method based only on FFT, this issue must be resolved. I will now explain the first program solution for the long-term derivative. In polar coordinates, the pole depends on longitude, as it turns out general formulation on polar coordinates because multiple here multiple value at the pole. Our key idea is to consider the pole as a unique point in the Cartesian coordinates. Cartesian to polar transformation is this rotation matrix. In particular, the computational components represent only Laplacian components. Next, I will explain the self-formulation vorticity and divergence of the pole. Their general expression on the pole, polar coordinates, is this form. This formulation. Those coefficients, this and here, cause a polar program because of infinity on the pole. However, if we return to the original formulation, and programmatic term, blue region and blue region cancel out. We compare the new SFT which can put the grid point at the pole and the previous SFT which cannot. Now we present only vorticity results. This panel shows the accuracy comparison between the new SFT and the previous SFT. The ordinate represent the sum of absolute errors. In particular, the new SFT is more accurate than previous SFT near the North Pole. In summary, objective 1, the polar coordinates expression that become singular at the pole can be reformulated in the following non-singular form. First, the longitude derivative can be reformulated using only rational derivative. Second, the velocity can be formulated using only rational derivative. So this idea cancels the polar problem on the SFT framework, and we can place spirit point at the pole. We now explain second objective, formulation isotropic wave number truncation. The left figure shows a nonlinear coefficient in SHT space. To prevent aliasing, we remove mode 2/3, the maximum wave number in the SHT space. This is called the 2/3 rule, and 2/3 of the maximum wave number is referred to truncation wave number. The middle figure shows spectral truncation in SHT space. Since all modes above the truncation wave number are removed, that truncation naturally satisfies the 2/3 rule. This truncation is known as triangular truncation and is isotropic. The right figure shows spectral truncation in SFT space. Also, the truncation satisfies the 2/3 rule in SFT space. It is no longer in isotropic in SHT space. As a result, so modes above the truncation wave number remain lead to aliasing and unstable time integration. Constructing isotropic wave number truncation based only on SHT, it must necessarily be SHT space. Fortunately, SHT space can be made from SFT space. For example, the SHT pattern of zonal wave number 4 and total number 5 is this distribution. The pattern of the constructed from 3 SFT. 1, 2, 3 SFT patterns. With suitable weighting, the distribution become identical to that on the left. The key idea of the wave number truncation method proposed in this study lies in applying the FFT to the associated Legendre polynomials, ALPs, that constitutes the spectral functions. For the ALP of degree n and order n, the maximum wave number of its SFT coefficient is n, and the spectral distribution depends on the property of the degree n. And the equation can be written in the form. The figure shows this in spectral space. For example, spectral harmonics of order n, and in SFT space, the spectral components appear alternately as present, absent. Based on this property, it is possible to directly transform SFT coefficients into SHT coefficients without expressly performing the SHT. Using the direct transform presented by Fukushima 2018, we construct a triangular truncation method based only on SFT. This method performs the calculation in just 4 steps. Step 1, transform from grid space to the SFT space using step 2, using a direct transform SHT coefficient needed triangular truncation obtained from the SFT coefficient. Step 3, using a direct transform obtain SHT coefficients required for triangular truncation from the SFT coefficient. Step 4, finally transform from SFT grid space back to grid space. The key point here is that wave number truncation method using only SFT is equivalent to the conventional triangular truncation method based on SHT.
You have about 4 minutes left.
Okay. I would like to talk about the result of 2 benchmark tests. The first benchmark test Williamson test case 2 for shallow models. We compare 3 methods. First, the new SFT. Second, the previous method combining SFT and SHT, and the third method, conventional spectral tracking methods. We simulate non-linear stationary jet program. We use FFTW and SpherePAC library. These panels show the results. The left column represents initial state, and right panel shows error at the day 10. The error distribution of the new SFT is similar to that of the previous SFT. The SFT solution clearly exhibits horizontal stripe pattern. The L1 norm of the new SFT is smaller than the other 2 methods. The second benchmark combine one gradient evolution and one spherical truncation for computational accuracy and speed. We compare new SFT by the FFTW library and SHT by the SHTNS. SHTNS use the world's fastest SHT algorithm. They are parallelized using Fortran query and OpenQuery. These panels show the computational accuracy results. The left panel represents computational accuracy, and the new SFT is more accurate than SHTNS. For those comparison error distribution, the new SFT is particularly accurate near the pole region. In SHTNS, polar noise due to the associated under transform property of the third recurrence relation. On the other hand, new SFT does not appear polar noise.
Here. 1 minute left.
Okay. There are vertical line on the new SFT due to rearrangement for rational orientation. The figure shows the alpha sign results. The color line and black dash line represent the new SFT and SHTNS. Also, SHTNS is faster, and the new SSD may become faster at the high resolution above 1,000 web number truncation. Moreover, the parallelization of SFD can still be improved, so it could be even faster. Finally, let me summarize. A key feature of the proposed method, compatibility with regular rational long-term grids, including the pole, potentially faster due to excellent parallel scalability and high accuracy by avoiding explicit Legendre transform. We may do novel contributions, but as it uses decided formulation at the core and eliminates for singularities, we can reformulate the equation into the pure safe form. Second, because it's constructed entirely with Fourier transform and ensure stable and accurate computation. We can formulate a spherical wave number truncation based on ST. Thank you for your attention.
Okay, there isn't time for questions, so let's go to the next speaker. So that is Daniel Oliveira, authors Jose Montero and Juan Espron. And this presentation is on matrix functions computation in hardware accelerators.
Hello everyone, my name is Daniel, and together with Jose Monteiro and Juan, I'm going to tell you about this research that we have done in matrix function calculation on hardware accelerators, more specifically in the GPU. A bit of background and motivation. Most of these goes into networks, graphs, and as they are represented in our codes, matrices. Nowadays, they are really heavily used. Some of their applications are, for example, what is viral, what does it need to become viral, to study epidemics, better vaccination methods, better borders blocking, communities identification, and many more. But nowadays, our infrastructure just keeps growing, and we are reaching a point where most classical numerical methods are starting to have a memory bottleneck, and most of them can't even compute. And all of this, if we would be able to solve it and use it on an hardware that is being mostly developed and researched nowadays, which is the GPU, the NPUs, together with AI, I think this would contribute a lot to the longevity of this solution. So, what exactly is the problem that we are trying to solve? As input, we have a matrix that is massive. I'm talking about millions of rows. And it's also sparse. With it, we want to calculate a selected entry of a certain matrix function. For example, the exponential, it can be the inverse, and many more. And hopefully, we can do all of these in a way that is scalable and hopefully greatly utilizes the GPU features. But what is the algorithm that can solve this problem? It is a Monte Carlo-based algorithm. We will be trading deterministic accuracy for scalability and parallelism. The way we are going to do this is we will be doing random walks as a way to approximate the powers of the matrix. Together with the Taylor polynomial series, we will be able to calculate certain matrix functions. So, as an example, let's start on the second row, and we will start by selecting one of the entries randomly according to their weights. In this case, we select the second to last column. With it, we will jump to the second to last row, and then repeat the process. Select one of the entries randomly according to their weight, in this case, the last column, so we will jump to the last row. And by doing this millions of times and then averaging it all out, we will be able to approximate the input matrix to the power of how many steps we did. This, together with the Taylor polynomial series, we can compute the matrix functions. But why is this algorithm difficult to implement? There are three main reasons. The first is branch divergence. To do a weighted random choice, normally what we do is from the weights, we accumulate them, normalize them, and then choose a random number between 0 and 1 and do a binary search. But this has a lot of branches, and specifically in the GPU, the way it handles branches is by executing both sides of the branch in serial and then only saving the value that matters to them. This happens because the GPU is CMD, single instruction, multiple data. Then there's the irregular memory access. In the algorithm explanation, as I said, we will be jumping from row to row. This will have a lot of cache misses because we won't be visiting the same rows we did previously. Then there's load balancing. It's a staple in this kind of problems. If there's a row that has a lot of edges and the weighted random choice takes a long time and most threads don't go there, this will have an imbalance and will make the code slower. So now that we have the basics, let's have a look at what other people did in similar situations. First, I will refer to Felipe Magalhães, which used the exact same algorithm, but in distributed memory. He used the CPU cluster together with MPY and saw a significant parallelism and scalability in this algorithm. So we are continuing his work. Then there's the Skywalker paper. It was made by Wang and a group of his friends, and they basically tested a bunch of sampling methods on GPUs that are supposed to be used by Monte Carlo and random walk algorithms. And from all of them, the one that caught our eye the most was the alias table. But what is the alias table? The alias table is a way to rearrange a weighted distribution in such a way that it only has a table with the same number of entries as the number of weights, and each entry has two values, a part of the original value that was there and its alias, the value that was used to fill. And this allows for constant time sampling. So how do we create the alias table? First, we find the target, which is the average of all the weights. We draw that line, and then from the weights that are above the target, we take the weight from them and put them on the ones that are below the target. By doing this and some other checks, we guarantee that in each table entry, there are only two values. The original one, or at least a percentage of it, and the alias, the value that was used to fill the rest. But now we need to implement this into our code. And there's actually a really trick neat we can do here. So for the data structure that we will be using, it will be CSR. Because as we are accessing the rows and trying to choose between their edges, this makes perfect sense for CSR, organizing them by row. And normally in CSR, we use the values to do the binary search. But here we are not doing the binary search. So we can simply take out these value arrays and use the two arrays needed to store the alias table, which is prop, which represents the percentage of this entry which has the original value, and the alias, the value used to fill the rest. This makes it so there's little change to our code, and it uses a bit more memory, but as a trade-off, it has a constant time sampling. So, to sample from the alias table, you simply choose one of the entries, and then a random value between 0 and 1, and decide whether you're using the original value or its alias. And this is really efficient on the GPU, as this uses constant number of operations in both sides of the branch, and it's only one branch, plus its constant time. So now that we have a solution, let's implement it and see the results. So for the experimental setup, we use the supercomputer Deucalion, which is some kilometers away from here, and they have for the CPU 2 AMD 64 core, and for the GPU they have the NVIDIA Ampere A100 with 40 gigabytes of VRAM. For the networks that were used as inputs, there are 4 important ones. 2 of them are based on the roads, all the roads from Europe and all the roads from USA. Both of these networks are very sparse. They only have an average of 2 edges per node. Then there's 2 of them that are based on websites. One is based on Orkut, which is a social network, and the other is LiveJournal, which is a news website. These are a bit more denser, although still sparse. They have an average density of 20 edges per node. So let's have a look at the CPU results. Here you can see a chart where it shows the average execution time for the 4 networks I set. In blue, you see the binary version, and in orange, you see the alias version. And in the CPU, we can see significant speedup from the use of the alias table. On these 2 first ones, which are based on the sites, the higher density ones, the binary version loses a lot of time doing the sampling. But on the 2 road ones, the binary version only has to look left and right and decide which one. So this ends up being not much of a speed up. And then come the GPU results, where everything becomes a bit more interesting. Now, all of a sudden, the speed up isn't as significant. For the website ones, the alias is still faster, but not by much. And in the road ones, the binary actually becomes faster than the alias table. But why does this happen? And this happens because of mainly one reason, which is cache. In the CPU, there's L2 and L3 cache. And this cache saves the rows that were visited previously. And in the GPU, we don't have that. So every time the GPU jumps into a new row, it has to grab that memory from VRAM. While in the CPU, you still have L2 and L3 cache. So the extra memory that the alias table uses ends up being a bottleneck on this, or in general in the GPU results, but more specifically in these lower density ones. Another interesting thing here to note is that the graph structure matters a lot. So not only its density, but it has a lot to do of how the graph is. In the example of the roads, normally roads, they are by group. You have a bunch of roads in an area, and then there's like a big road that is like really fast, or maybe there's like a bridge that separates two like conjunctions of words. And this is really great for the cache. But for example, on the websites, normally there's hubs on websites. There's like a page with a lot of like connections. And so what ends up happening is that you have a lot of chance to go into the hub. And then when you go into the hub, you spend a lot of time doing the binary search. So the graph structure really matters when choosing whether to use the alias table or the binary version. But independently, if you look at the values, the GPU results were always faster than the CPU results. This means that for this algorithm in specific, it is well suited for a GPU. Not perfect, but well suited. With it, I will finish my presentation. Thank you so much for listening. And if you have any questions, go ahead.
Any questions?
Let me ask naive questions. So could you go back 2 slides? So what is the difference between the 4 models and what is the horizontal axis?
Sorry, could you repeat?
What is the difference between among these 4 models?
The 4 things you see here are the networks we used as inputs. And the models are the colors. So in blue it's the binary version, and in orange is the alias version. And the 2 networks on the top are the website ones, and the 2 on the bottom are the ones that are based on roads.
I see. So whether there is improvement or not depends on the such networks, you mean?
Right.
I see. And could you also go back to 1 slide? I see. So for CPU, so always you have improvement.
Right.
I see. Thank you.
No problem. Any other questions?
Yes. You compared binary search and alias approaches, and I wonder what are the difference in accuracies?
Okay, that's an interesting question, and basically, together with all of these times, we also store the precision, and we see minimal difference. I think the binary version is like slightly precise, but it's really insignificant. We were getting precisions of like 10 to the power of -6, and the difference was basically 3 times 10 to the power of -6 and 2 times 10 to the power of -6. So there was a little difference, but it wasn't significant.
What bits you are using on GPU and CPU? Floating point.
FP32.
FP32.
Yeah. We also tested with 64 double, but we saw no difference in precision. It's something that is actually pretty interesting, and I couldn't really find a reason why. Basically, when we swapped from 64 to 32, we expected the precision to lower, but in the CPU results, it lowers it a bit, but in the GPU, it doesn't. and we thought that was really interesting, and we tried to search why, and we discovered, for example, FMA, which is basically they can multiply and then add all in a single like CPU instruction. And then we tried deactivating it, and it still had a big precision. So that's something that we are not sure why, but for some reason the GPU keeps the precision of when we use 64 to when we use 32.
Can you push even further to FP16, even FP8?
We didn't test that because we thought that was really going to lower the accuracy to the point where there wouldn't be much reason to use this.
Okay, let's thank the speaker again. Time
Okay,
for the next talk. Yeah, Matsufuru-san.
So the next talk is presented by Elise de Donker, the previous chair. So I chair instead of her. So I'm Hideo Matsufuru, co-chair of this workshop. So could you share the slide?
Go to the screen you're going to below it.
Could you? Oh, okay.
Can you see it?
Yes.
All right.
Could you wait a little bit?
So this presentation.
Just a moment. So there is no slide on site. So
no slide.
Just a moment. So just wait for a second.
What is it?
Is it okay?
It's okay. You can start.
Okay.
Thank you.
Okay,
all
so
right,
please
thank
start.
you. So we handle the numerical evaluation of three-loop Feynman diagrams, in particular the ones with nicknames baseball and running shirt, using GPU-accelerated QMC integration and extrapolation, and based on sector decomposition. I thank my co-authors, Daisaka, Ishikawa, Kato, Nakasato, and Yuasa. So I will start with an introduction to Feynman diagrams and give motivation for their calculations leading up to loop integrals. All right. So we need we need reasonable accuracy for the theoretical predictions of the cross-section for particle interactions in view of improvements in the technology of the high energy physics experiments. Indeed, the general and analytic treatment is not possible for general mass and momentum values, so we resort to numerical approaches for the integral approximation. Here, the number of dimensions and the degree of difficulty of the integration increase as the number of lines and loops increases in the diagram, and that leads us to the use of multivariate integration methods in the presence of singularities performed on high-performance computing architectures. So we will handle two case studies. On the left of the figure, we have the diagram that's referenced as the baseball diagram, and on the right, the running shirt diagram. So they have 3 loops and 6 internal lines. The loop integral representation uses the Nakanishi, Svitanovich, Kinoshita formalism, and the scalar loop integral is given by the blue equation, which is an integral over the n-dimensional unit cube Kn. The XR is the corresponds to the arc line in the diagram. U and V are polynomials. The I rho is an infinitesimal imaginary mass value. So N is the number of lines, L is the number of loops, and nu is the space-time dimension, which is 4 minus 2 epsilon. So that brings the equation into as a function of a parameter epsilon. So for, in our cases, L equals 3, N equals 6, then we just substitute those values. In the dimensional regularization method, we deal with an expansion of the integral in powers of epsilon. So here we start with the term in 1 over epsilon squared. And then we focus on the behavior of the coefficients as a function of S, the squared momentum P squared. And we compute this for the equal mass case, where all the masses M are equal some value M. So transformations serve to simplify or smoothen the behavior of the integrand. We perform a transformation. XR is YR for the first 4 variables, and then X5 brings in a Y5 and a variable Z, and there's a notation Z bar, which is 1 minus Z. So that expresses the U function and the W, which is as polynomials in terms of the new Y variables. So we're interested in the coefficients. The coefficients of the C minus 2, C minus 1, and C0 can be expressed, well, fairly simply, but that is as functions of these J functions that that are functions of the squared momentum S. For S, we can say that the S-dependent functions have a threshold. The main threshold here, which is a physical threshold, is at 4m squared. And then there are some other unphysical thresholds. Using sector decomposition, the integration domain of the integral I is divided into 5 factorial, which is 120 regions, or alpha, where alpha is a permutation of the quintuple 1, 2, 3, 4, 5, and associated with those subregions are subintegrals I alpha. Now, taking symmetries into account, only 15 subintegrals need to be computed. So this was about the leading term coefficients. We will concentrate here on the coefficient C1, which is difficult to determine, and we calculate it numerically. The sector decomposition procedure is used here, and it's based on a variable transformation from the Y variables into variables S, T, U, V, and W. So the U function is a sum of monomials we saw, and its structure dictates categorization of the integrals and sectors into a type 1 and type 2 form. So using this transformation, we have expressions for U and W for the two types. And that is done within each sector alpha. The sector decomposition final result then expresses the integral as the sum of integrals I alpha. The summation, in the summation, alpha runs over the 15 permutations that are listed here. For the integrands, then, we also use the subdivision in the type 1 and type 2 integrals as a function of epsilon. The integrands denoted by the capital F, well, there's some listed here for as the integrals of type 1. The F is given as an expansion in epsilon. Here is the constant term, then a term in epsilon and an order of epsilon squared. And then further examples are for integrals of type 2. The computational tools we use, there are three that are mentioned here. These are lattice rules, transformations, and extrapolation. The lattice rules form a sequence embedding. So it's a sequence of rules that are based on a basis rank 1 lattice rule, which is a sum of function values of the integrand f at values determined by a z vector, which is called the generator vector of the rule. Okay, and then the rest of the sequence consists of sequence elements QR, F, where the points of QR are embedded in the points of the next rule QR plus 1. All right, for transformations, for the integral, well, lattice rules are defined for periodic functions. So we use a periodizing transformation. It's called psi p of t here, where the psi function is by CD, work by CD, and we use order 6. This transformation also helps alleviating boundary singularities. So the derivative here, psi prime p, is assigned to the 6. Then for extrapolation, we use a nonlinear method of the epsilon algorithm. The computation produces a triangular table. The entry sequence, the left column, consists of integral approximations, and then each subsequent column is generated from neighboring entries of the previous columns. So the scheme is given here, where the element nu is computed in terms of E0, E1, E2, and E3. And then also a distance or sort of error estimate is associated with the new element as a sum of absolute values of differences of the E values and the new value. So here is a possible sequence of the computation of the table. So we have the first the column here, 1, 2, 3, etc. The dots represent sort of sentinel values that are set to infinity to make the formula work to get the second column here of the table. Then once we have that, we can use, for example, elements 3, 4, 6, 9 to compute element 9, 8, 11, 14, and 7 to compute element 15, etc.
5 minutes are left.
Thank you. We have plotted results for the two types of diagrams, baseball, BB, and we focus on the coefficient C1 as a function of the squared momentum as is p squared. So in the first two figures, we have plots of the C1, the real part and the imaginary part, real in red and imaginary in green, as a function of S. So there's at the threshold, which is 4 here, 4m squared, the real part shows a peaked behavior, and the imaginary part that was 0 before comes in at this point. So this is for the baseball, and then running shirt is in figure 3, which is similar. Then since there is irregular behavior at s equals 4, we in figures 4 and 5 we show in more we enlarge the figure around this point. So this is for baseball, and then here for running shirt, C1. And then we have a figure of the baseball, C1 real part, and next for the imaginary part for the 15 sectors. So these are, although the original curves are kind of haphazard, the summation behaves pretty nicely. So in conclusion or summary, this highlights some of the points. We obtain the energy dependence of the loop integrals under consideration. Higher order corrections can contribute to accurate theoretical predictions of the cross-section of particle interactions, and these are fundamental to match increased accuracy in high-energy physics experiments. The dimensionality and degree of difficulty increase with the number of loops and lines in the diagram, and generally it's not possible to treat multi-loop instances with arbitrary masses and momenta. Therefore, we focus on numerical approaches. So for the integration, lattice hues are used with suitable transformations, which provide an important tool also for boundary singularities, and are implemented because of their regular structure. They can be easily implemented on GPUs using high-performance computing. All right. Are there any questions?
There is 2 minutes for questions. Do you have any questions? So let me ask a question. So your method seems very sophisticated, but so there is another diagrams in the same order, maybe many. So is this procedure applicable to other diagram automatically, or you need some manipulation?
Well, the basic idea is the same, but there will be, for other diagrams, different types of sectors and integrals and integration difficulties.
I see. Any other questions?
All right.
So if not, thank you very much again.
Thank you.
So now the session closes, and the second CSHPC session will start at 14 on site and maybe 13 UTC. See you again.
Thank you.
Thank you.
Thank you very much for participation.
Matsufuru-san,
Yes,
will you chair that session at 2:00? Or should I?
I will be possible to chair.
You will? Okay.
Yeah.
Thank you.
Thank you very much.
Yes.
See you.
See you.